identify. Okay, so 2.1 is all about the additive property of equality. You never need to know that phrase in the future. What that really means is solving one-step equations with addition and subtraction. And there'll be multiple steps by the end of the section, but we start with one set. And just in a big picture sense, told this in my last class, I really want this to be important. I completely understand that that is the entire point, that the first problem you could just look at and say, the answer is 4. I know it. I don't care. I don't want you to write it down. I don't want you to say, I got it. The point here of starting out with very easy problems is that you learn a method, a system of organization that you can carry forward with you into the more challenging problems. Because even by the end of today, we're doing 2 or 3 step equations. By the end of tomorrow, we're doing lots of step equations, parentheses, distributing the negative, combining like terms, moving it over, fractions, decimals. I'm throwing everything at you quick. So the point of today in starting with really easy problems is to learn a method, practice it with the easy problems, so as the difficulty grows, you have a good system of organization. The analogy I gave is it's like going to the gym for the first time. You don't grab the most weight you can possibly lift off the ground and awkwardly go exercise, right? That creates bad habits. You grab a little weight that you can control and you work on balance and breathing and motion and keeping right angles and all the healthy habits so that as you increase in weight, you have good form and you don't sprain muscles and do bad things, right? It's the same thing with math. I know a lot of people's reaction right away is the answer 4, I got it, done, skip, right, answer, done. The point is to write a nice system of organization to carry forward, okay? So first I'm just going to define a linear equation in a really bad way. But again, it's because in the future you'll know the vocabulary to deal with it. Okay? So specifically, a linear equation has one variable. That's not even the way I wanted to say it. Okay, so the variable, and I'll put a little s in parentheses, has an exponent of exactly +1 So the big thing is, it has to have an exponent of exactly +1. Even more specifically, the variable can't, and you'll see why later, can't be under square root. The reason is, that's a fractional exponent. Square root would be x to the 1/2. That's not x to the +1. It can't be under a division bar, right? We just saw if it's under the division bar, that's a negative exponent, right? So 5 over x, that would be x to the -1. And then, or an absolute value, and the list goes on and on and on and on and on. Dot, 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 right? So there's this never-ending list of nonlinear equations. The linear equations are pretty straightforward and beautiful. I'll give you some examples. So here are linear equations. And this is what we're going to study for the first half of the course, or the first third of the course. And then the rest of the course, we're going to study nonlinear equations and how to deal with those. So here's linear equations and nonlinear. So linear equations would be something like x plus 5 equals 6, It could have lots of x's. 2x plus 3 times 5 minus x equals 6x plus 5. It could have multiple variables. Y equals 2x minus 6. Okay, it could have even more. It could be, x plus y plus z equals 11. Right, this is one-dimensional, two-dimensional, three-dimensional, but it doesn't matter. They're linear because they all have to the positive 1 power. And they're all by themselves. They're not multiplied together. Things that are nonlinear. X squared plus 2 equals 5. 2xy plus 6 equals 11. Square root of x equals x plus 1, right? One of these is linear, the other one's not. 5 over x equals y, or one last one, there was one more, absolute value of x plus 2 equals 3. And again, this, the whole idea of what's linear and not linear will become more clear when we get to chapter 3 and we're talking about linear equations and graphing them in 2 dimensions and the relationship between x and why linear growth is so useful and very extremely common in life. Okay. But yeah, so the first questions on your homework will ask you, for numbers 1 through 10, they'll say, just say whether the problem is linear or non-linear. Don't solve it, don't anything. I'm going to specifically bring up problem 7 because I think it's a poor problem, but it highlights a common mistake, so that actually makes it an exceptionally wonderful problem. Okay, so number 7 has, I don't know why I'm looking for it, I actually have it memorized, but number 7 is square root of 2x plus pi equals 0 point, I think it's 3 or 8 or 7, 3. Okay. So the question here is it linear or not? And I would say that depends on how sloppy your handwriting is. Why do I say that?
Is that because of the square root, if they go over the...
Yeah, exactly. So the way the book wrote it, you would never write, and no math teacher would write it this way. Every math teacher would write it either as x square root of 2 to be clear that the x is not in a square root. We'll spend a whole chapter on radicals and on roots, and you will always write the things that are not in the radical out front. Or, to be clear, we would put a little e at the end to say it stops here, right? Because commonly, people copy this down onto their homework and they write this. So yeah, on your page you wrote that, and on your page it's a nonlinear equation. However, in the book, it was a linear equation, because it doesn't matter what number is times x, plus what number equals what number. I mean, yeah, the numbers look a little more crazy, anxiety building up, but this is the same thing, or analogous to this. Right? And that's a huge part of math, being able to compare things and say, oh, that's just big scary numbers, but really, big picture, it's the same as this easy thing. And I mean, that's all math is learning the easy stuff and then getting a harder problem and saying, oh, it's the same thing, just one little baby step harder, right? And that's all math is. Every time it's one little step until you get to the top of the mountain. Okay? So this one is linear, and the reason is that square root does not go over the x. So the answer here would be linear. Okay. The rest I think are a little more clear. Okay, so I'm just going to give you one way I think about linear equations, and then I'll show you how to solve them, and then I'll do a bunch of examples. Okay, so there's two ways to see it. I've always thought about it as you have a scale that's balanced. I'm not a good artist, I don't pretend to be. I know pretend what that means, but actually too, that was totally wrong. Okay, so if we got a balanced scale, we can add the same weight to both sides. So even if we have two different things, okay, let's say I have a star there, and we have a smiley face in this one, okay, but the scale's balanced, okay? I can add the same thing to both sides, or take away the same thing from both sides, and it will always stay balanced. So I could add a little marble to both, regardless of how much each side weighs, regardless of what is in each side. If it's already balanced, I can put the same thing in each side. I could put a little square block, as long as it's exactly the same color. I could take a triangle, and I could add it in, as long as the triangle is the exact same. And the big idea is, if the scales are already balanced, I can add, subtract, the same thing to both sides, and they stay balanced. And this is how we're gonna build up the entirety of chapter 2, is you can do the same thing to both sides, almost regardless of what you're doing. You can flip both sides over. You can add a number to both sides. You could square both sides. You could take the absolute value of both sides. You could do almost anything to both sides, as long as you do the exact same thing to both sides. They'll stay equal, right? There's no way you could take 5 equals 5 and take the square root of both sides and then one side change, right? The square root of 5 will always be equal to the square root of 5, because 5 is the same as 5, right? So if you do the same thing to the same thing, obviously you get the same thing, right? And that's the big idea here. So another one is if you already have equal equations like 6 minus 2 equals 2 squared, right? Obviously, you know, we can see 4 equals 4. Got it, we know this is equal. Okay, if you already have both sides equal, you can do whatever you want to both sides. So let's say 6 minus 2, I want to add 2 to that side, equals 2 squared plus 2. I don't even need to figure out what those numbers are, I know it's equal. Because I started with 4 equals 4, and I added the same number to both sides. So you can add, again, add, subtract, at the same operation. You can add the same thing to both sides. And it stays equal. So let's do some problems, and I'll show you how. You have to show your work on my homework. On the test, you can do it however you want. On this homework, and this one alone, I'm grading you on whether or not you do it my way. And I say this one alone is a 2.1, 2.2, 2.3. After that, you can do it if you want. Okay, but these ones, you have to try it my way. All right, so, quick example. Just making this one up. The rest of the examples will be out of the book. Okay? So what could we cleverly add to both sides to get x by itself?
Plus 3.
Yeah. Yeah. So we add 3, right? We have a minus 3, or you could smatto and see we have a plus and negative 3. Either way, we have a negative 3. We have a whole of 3 we need to fill in. So if we add 3 to both sides, cancel that, now we have x equals 11, right? That's how I want you to show your work for these sections. Okay, I'll do a couple more examples with you, and then I'll give you some time to work on these. Here's number 20. Okay, so 18 plus z equals 14. Right, what will we do to both sides? Yeah, right, we've already got a z here, there's one z, and all we need to do is get rid of the number. So we subtract 18 from both sides. We need to show it like this. Cancel that out, we get z equals. Okay. Another one is now, you can separate this and call these multi-step ones. Whereas step 1 is just simplification. Okay, so exactly what you've been doing in chapter 1. Okay, so now we're building up chapter 1 plus new material from chapter 2. So 46 looks like this. Okay, so what's the first step? Yeah, for sure. Yeah, so first we're going to combine like terms. When I circle my like terms, I always circle the sign to the next to them, or you could model first. That to me tells me each one whether it's negative or positive. So negative 3x plus 4x is, oh, that's nice, just 1x. And after you simplify any linear equation, the worst it can possibly look is like this. And every linear equation that we solve in the entirety of chapter 2 and the entirety of this course will look like this. After you get rid of the parentheses and combine like terms, you will have some x's plus some numbers equals some x's plus some numbers. So get insanely used to solving this equation, right? Regardless of what the numbers are, if they're fractions, if they're decimals, doesn't matter. Okay, but this is what every linear equation in algebra will boil down to. And who knows, this might be missing, like in this case. We have some x's and some number equal number, right? Or maybe this is missing. We have x's and number equals x's, right? But that's what every single one is going to boil down to. So we already combined the like terms. Next step is? I heard add. Yeah, add 5. Right, that cancels and we get x equals 14. Okay, so I'm going to take that to the extreme and do one last problem where now there's variables on both sides. So the end of 2.1 looks like problems with problem 50 here. 4r minus 3 equals 5 plus 3r. Okay, so we got our first this is a real linear equation here. What's the big idea for solving this situation? To get what on one side? So trying to get all of the variables on one side and everything else on the other. Doesn't matter what else there is, but usually it's just numbers. So get all the variables on one side. In general, it's smart to get it on the side where there's more variables, so that way you have a positive amount of variables, but it doesn't matter. You could always arbitrarily put them on the left if you're just comfortable with left side. But how would we do it?
Minus 3.
Yeah, so minus 3r, minus 3r. So that gives me in r, this should always cancel, minus 3 equals 5. And then one more step, somebody other than Nick. Plus 3, thank you, Aaron. So we got plus 3, and this cancels, and we got r equals 13. Okay? So that's what it's going to build up to at the end.
No, the answer is 8.
Plus 3.
It'll be plus 3.
Plus 3
equals 8.
I'm there. There we go, see? Alright.
The other 3.
Alright. So yeah, so this is what it's always going to build up to. There's even going to be problems on the homework where it's like 3x plus 5 minus 2x plus 4x equals 7 plus x minus 6. So there's going to be a lot of x's and numbers all added up on both sides. That's what we're going to build up to today. But there's no multiplication or division. Okay, 2.2 is when we bring multiplication or division in, and then the big idea from this is always it takes 2 steps to solve. One step is getting all the variables on one side, numbers on the other, and the last step is whatever number is next to the variable, you just divide by it, right? That's it. So variables on one side, numbers on the other, divide by the coefficient. Done. That's all every linear equation ever. There's no creativity involved, okay? There's a beauty in the simplicity. All right, So yeah, start working on that, ask questions if you want to, take a little break, get some fresh air, do some problems, ask for help, and I'll be just